Hello everyone, welcome back to Z Physics. Today we're going to be solving the 2019 AQA Paper 1 A-Level Physics multiple choice questions. Now for the purposes of this video, please have a look at the paper and the link in the description. And on my digital whiteboard, I'm only going to be showing you how to solve each problem. Okay, well, let's get started with question 8. Question 8 is all about beta decay. So let's think about what particle X and particle Y are. First off, in this beta decay, we have a proton which turns into a neutron. Now, in the process, there was going to be an emission of a W plus boson. So X is actually going to be a W plus boson. And Y is going to be an electron neutrino, like so. Therefore, the correct answer is A. Question 9, we have an electron which is interacting with an atom, and it collides with the orbiting electron, and the orbiting electron goes up in energy state. Now, this can only happen when energy is transferred to that electron. Therefore, the correct answer is D. Question 10. This question is all about Einstein's equation. So we're going to use HF is equal to the work function plus the maximum kinetic energy, where HF, of course, is the energy of the incoming photon. H is just Planck's constant and F is the frequency. Okay, so in this case, we're really looking for the kinetic energy. So K max will be equal to HF minus the work function, i.e. K max will be equal to Planck's constant, which is 6.63 times 10 to the power minus 34. Our frequency is given in the question as 2.0 times 10 to the power 15. Take away the work function, which is 4.6 times 10 to the power minus 19, which is going to give us an answer of 8.66 times 10 to the power minus 19, which is about 8.7 times 10 to the power minus 19 joules, i.e. the correct answer is C. Okay, so question 11, all about the momentum of a photon. So remember, the equation that we need to use is that the energy of a photon is equal to the momentum of a photon times the speed of light. So E for any photon is equal to HF, so that will be equal to P times C. In other words, the momentum will be equal to HF divided by C, which is 6.63 times 10 to the power minus 34, times the frequency, which in this case is 1.5 times 10 to the power 15 hertz, and we're going to divide that by the speed of light, 3.0. times 10 to the 8, which is going to give us about 3.3 times 10 to the power minus 27. In other words, the correct answer is C. Okay, question 12, all about coupled forces and torque. Now, a torque couple will consist of two forces which are equal in magnitude, opposite in direction, they're coplanar, and they will produce rotational motion. For instance, if you have a ruler or a bar or a crankshaft or something like that, if you apply two forces in such a way, it will start to rotate around an axis. However, those two forces cannot produce translational motion. Translational motion is just like this. It cannot move it just from side to side, that they can only produce rotation. So this sort of movement is impossible with coupled forces, and therefore the correct answer is C. So question 13, this question is all about distance time graphs, and remember your distance traveled is equal to the area underneath the graph. So in this question we're given two graphs, one for Q and one for P. So for Q we can calculate the area, which is just a triangle, so a half times base times height, which is equal to a half times 8 times 40, which is 160 meters. Now for P, the expression is just below, so dP is equal to a half times 2 times 20. This is the triangular portion of the graph plus the rectangular portion of the graph, which is just 20 times 5, which is going to give us 120 meters. Now let's take away those two numbers. So obviously 160 take away 120. We're going to have a distance between the two cars being 40 meters, i.e. the correct answer is A. Okay, question 14. This is a really interesting one. So let's think about the forces involved acting on, let's say, the 0.20 kg mass prior to the cutting of this string. So first off, we have a spring force which is acting upwards. So let's just draw that. This over here is the force from the spring. Let's just call that force, let's just call that F subscript S. We also obviously have the weight of the 0.2 kg box. So that's going to be, let's call that the weight. Let's call that weight 1. And we also have the weight of the 0.1 kilogram box also acting downwards, which is, let's call that weight 2. Now, because initially the system is in equilibrium, we could write down an equilibrium equation, and we could say that the force of the spring is equal to the combined weights, like so. So we can say that the force of the spring is going to have to equal 0.20 times 9.81 plus the other weight, which is 0.10 times 9.81. And if we were to add those in, we're going to get about 2.943 newtons. Now let's think about what happens after we cut the second mass. So let's just say that after cutting, the spring force will remain absolutely the same, and the weight of the 0.2 kg mass will also remain the same. In other words, there are only going to be two forces acting on the 0.20 kg box, and that will be the force of the spring, which will be the same at the very instant that it starts to accelerate, and the weight 1. So let's just say that the weight of the weight take away the force of the spring is equal to the mass times acceleration. This is just Newton's second law, that all the forces combined acting on a system are equal to the product of the mass times the acceleration. So what I'm going to do is say that the weight is just equal to 0.2 times g. And we already know the spring force was 2.943, and that's going to equal to the mass, which is 0.20 times the acceleration. So we can directly rearrange for the acceleration, which is going to be equal to 0.20 times 9.81, take away 2.943 divided by 0.20. And if we were to put this into a calculator, we are going to get negative 4905. Now the magnitude of this acceleration is just 4.905 meters per second squared. Let's not forget the unit, and the sign just simply dependent on what we take for positive and what we take for negative. But either way, the correct answer is B. So question 15, we have a lift which is decelerating, and it has the following forces acting on it. First off, we have the weight which is acting downwards, we have a frictional force acting upwards, and we also have some tension which is also acting in the upward direction. Now it's important to know that this system is not balanced, and in fact this whole lift is going downwards with an acceleration Now let's apply Newton's second law and let's just add all of the forces. So in one case we have mg, which is acting straight down, and let's take away the forces acting in the other direction. So it's going to be minus F because it's acting in the opposite direction, minus T, which is acting also in the opposite direction. And these are all the forces that are acting. Now, because of Newton's second law, this is equal to the mass times acceleration of the lift. Now let's arrange for the tension. So I'm going to bring the tension on to one side. So we're going to have that the tension is, so if I bring that up to here, this means that I have to bring that up to there and then change the signs of it. So that's going to be mg minus ma minus the frictional force, which is equal to m g minus a minus the frictional force, which means that the correct answer is D. Question 16. This question is all about Newton's second law, which remember states that the rate of change of momentum is equal to the net force acting on an object. Therefore, if an object is free falling and the only force acting on it is the weight, the rate of change of momentum will be equal to the weight of that object. Therefore, the correct answer is D. Question 17, this is a really good one. So we have an electric vehicle and we have the electric motor is producing a constant force. What is the variation of the power produced by the electric motor with time? Now it's important to know that the power is obviously not equal to the force. The units are not the same, but the equation that we need to use is that power is equal to force times velocity. Now the force does remain constant, however, how does the velocity change? We know that constant force, should we just write this over here, constant force means constant acceleration. And that means that the velocity will be increasing linearly from zero, therefore the power will be increasing linearly from zero as well. And therefore the correct answer is B. Okay, question 18, that is all about power. Now, first off, power is a scalar quantity. It does not have a preferred direction. Second of all, power is measured in watts. Now, what is the fundamental unit of the watt? Well, remember, power is nothing but the energy has been transferred over time. Now, let's break down the individual units of each of those quantities. So, energy, let's pick our favorite formula for energy. Mine in particular is just a half mv squared divided by T. So, let's work out the units on the top and the units at the bottom. The half has no units, so I'm not going to consider that. The units for the mass are kilograms. The units for v squared are ms to the power of minus 1, all of it squared. And I'm going to divide that by seconds. This is equal to kilograms meters squared s to the power of minus 2 divided by s. Now, s to the power of minus 2 divided by s is, of course, equal to kg m squared s to the power of minus 3. And therefore, the correct answer is C. Question 19, all about stress. So remember, stress is equal to the force applied divided by the cross-sectional area. Now in this case, we're applying 50 newtons over a cross-sectional area of 1 square millimeter. Now 1 millimeter squared is equal to, so let me just write that down in full. So 1 millimeter squared, so this will be equal to 50. Now 1 milli is actually equal to 10 to the power of minus 3. All of it is squared, so this will actually be equal to 50 divided by 10 to the power of minus 6, which is approximately equal to 5.0 times 10 to the power of 7. And This means that our correct answer will be C. So question 20, this is all about Young's modulus. So Young's modulus is defined as stress over strain. In other words, this is equal to the applied force divided by the cross-sectional area divided by our extension and the original length. Now just tidying up this fraction, we get that F over X multiplied by L divided by X, because dividing by a fraction is the same as multiplying by the inverse. Just rearranging for X, we get that X is equal to F times L divided by X times E. Now, out of those combinations, D is going to give us a minimum extension X, because E has been increased 4 times. The area has been increased twice, and the length has remained the same. So out of all of those combinations, and with the laws of proportionality, this is the best option. Okay, so question 21. Now we have the speed of the belt, which is 0.4 meters per second, and we also have the width, which is 0.1. Therefore, the cross-sectional area in 1 second is simply going to be 0.4 multiplied by 0.1, which is equal to 0.04 meters squared. Now, because we know that 1 square meter corresponds to a charge of Q, therefore 0.04 is going to correspond to 0.04 Q, therefore the correct answer is B. Now the next question, question 22, is all about the definition of an electron volt. Remember, 1 electron volt is defined by the energy gained by an electron once it passes through a region of 1 volt. Therefore, if I had an electron moving between those two plates, it will gain 1.5 electron volts. Now, what could possibly gain 3 electron volts, which is double that? Well, out of all of those particles that are listed, only one has a charge, a net charge of plus 2e, where e is the elementary charge, and that is the alpha particle, because an alpha particle consists of 2 protons, which have a charge of plus 2e, and 2 neutrons, which don't have a charge and don't really affect the acceleration. But once again, it's an alpha particle because it has a charge of plus 2e, therefore is going to gain 3 electron volts of energy. Okay, question 23. We're looking for the potential difference between this point and essentially the ground. So let's figure out the potential difference across this component, then across this component, and let's add them up together. First off, because V is equal to IR, this means that the voltage across this resistor will simply be equal to 2 times 10, which is equal to 20 volts. Now, because the currents need to add up according to Kirchhoff's first law, we have 4 amps going in here and 2 amps going in there. In total, we're going to have 6 amps going through here. So, which means that our second potential difference, let's call that V2, will be equal to 6 amps multiplied by 20 ohms, which is equal to 120 volts. Now the potential difference between the ground and this resistor here will actually be equal to 140 in total, so 140 volts. Therefore the correct answer is D. Okay, so the next question has a little bit of a trickier wording. So we have the power supply is connected across this voltmeter that was somehow connected to series to this resistor. Well, we are given that the voltmeter reading has gone up by 2 scale divisions, which means that the reading across the voltmeter is 2 volts. We're also given the resistance of the voltmeter, which is 4 kilo ohms or 4,000 ohms. Okay, well, now we have the following circuit. We can actually think of this voltmeter essentially just as a resistor. So if we have 2 volts across here, due to Kirchhoff's second law, this means that we must have 18 volts across there. Now, because of the ratio of the voltages compared to the resistances, if the PD is 9 times as high, the resistance also needs to be 9 times as high, which would mean that the resistance across the resistor would be 36,000 volts, i.e. the correct answer is B. Question 25, we have the following arrangement with the 2 types of wires, P and Q, that are connected in series and then connected to a power supply. Now, which 2 quantities are going to be the same? First off, the first quantity which is going to be the same is the current, and that is due to Kirchhoff's first law. So the sum of the currents entering a junction is equal to the sum of the currents exiting a junction. The amount of current that goes in will have to be the amount of current that goes out. Therefore, the current will be the same in both P and Q. Now, because they're made out of the same material, additionally, the resistivity will also be the same, because the resistivity only depends on the type of the material and not on the shape or the size of the material. Therefore, the correct answer is B. Question 26, we have the following circuit over here, and additionally what has happened is that we have increased the temperature of the thermistor. Now remember, the temperature, the resistance against temperature graph for a thermistor has a similar shape. So as the temperature is increasing, the resistance is decreasing. This circuit is essentially an application of something called the Wheatstone bridge, in which, when it is balanced, meaning that the voltage across it is 0, the ratio of the resistances is as follows. So the resistance of P divided by the resistance of Q will be equal to the resistance of R divided by the resistance of T. Now, if the ratio is to remain constant, the only way to do that is if this component is going down, the resistance of the thermistor is going down, this means that the resistance of the resistor has to go up. And that is the only way we can restore the voltage back up to 0. Okay, question 27, all about efficiency. Now remember, our efficiency is defined as our useful energy divided by the total energy. Now, the useful energy in this case is just simply gravitational potential energy. Because the gravitational potential energy is mgh and W is mg, we could write down that our GPE is actually equal to W, the weight, times the height. And our total energy is just the electrical energy, which is VIT. If you're unsure where this expression comes from, so power is energy per time, therefore energy is power times time. Power is V times I times T. And therefore the correct answer is C. Okay, question 28, which is all about this rotating object. Now, the rotating object completes n revolutions per second. So this means that the frequency f is actually equal to n hertz, because the frequency is defined as the number of cycles per second. Now, the velocity of this object will be equal to the distance traveled, which is the circumference, and the circumference of this circle is just 2 pi r divided by the time period. We could also write that as 2 pi r times 1 over the time period. Hang on a minute though, 1 over the time period, this is just our frequency. Therefore, the speed will be equal to 2 pi r f. Additionally, because our frequency is just equal to n hertz, we could just rewrite this as V is equal to 2 pi r multiplied by n. Okay, well, the kinetic energy is equal to a half times the mass times v squared. So that's going to be equal to a half m, and let's square out 2 pi r n, all of it squared. So that's going to be a half m times 4 pi squared r squared n squared. Let's cancel out those guys, and what we're left with is 2m pi squared r squared n squared, and the correct answer being C. Question 29. A question for simple harmonic motion. We have a graph of the displacement against time, and we've plotted a graph for one time period. The question is asking us, what will the graph for the kinetic energy look like? Now, first off, the kinetic energy can only be positive. So this is really important. Remember, Ke is equal to a half mv squared. A half is a positive, the mass is a positive, and v squared will always be a positive. So all the options that go into the negative portion of the graph for kinetic energy will not be correct. Additionally, the graph starts at 0 displacement. So when the displacement d is equal to 0, v is equal to a maximum, therefore the kinetic energy will also be a maximum. Therefore, the graph will look like so. The kinetic energy will start here from a maximum, then it will start oscillating. So, question 30. This question is all about phase shift. Now we can calculate the phase shift as the relative difference in the time period divided by the time period times 360 degrees. Now, because we're talking about the oscillations of A, I'm going to be using the time period of A over here. Now, delta t will be equal to 2.00 minus 1.98. That's my delta t divided by 2.00 times 360 degrees, where 360 degrees is one oscillation, and that is equal to 3.6 seconds. So this means that after exactly 100 oscillations, they will be in phase. However, that's not what the question is asking. It's asking us for the number of oscillations just before that moment, and the correct answer for this is one less, which is 99. And this is a great example of how carefully we should be reading the question. Okay, question 31. We're almost there, guys. So this question is all about the equation for the time period as related to the mass in a simple harmonic oscillator, and this formula is found in your A-level physics insert. Now remember, the time period is equal to 1 over the frequency, so we can say that 1 over the frequency is equal to 2 pi the square root of m over k. Now we can flip both sides of the fraction, and we can say that the frequency is equal to 1 over 2 pi the square root of k divided by the square root of m. Because of that, the frequency is proportional to 1 over the square root of m, and because the square root is defined as the quantity being raised to the power of a half, the frequency is proportional to m raised to the negative half power. Therefore, the correct answer is A. And let's tackle our final question, 32. Now, this question is all about resonance. What will happen to the resonance graph if we were to introduce damping into the system? We can see that the acceleration is a maximum at this resonance frequency, which is 100 Hertz. If we were to introduce damping into the system, two things happen. First off, the amplitude is lower across all of those points, so we can see that this curve is spread out. Additionally, the peak is a little bit shifted towards a lower frequency, which is a frequency to the left. So as long as we have mentioned those two rules, we're absolutely fine. So just double check, yep, the peak is shifted to the left and the amplitude is lower. Therefore, the correct answer is D. Okay guys, so we've tackled all of the multiple choice questions of this paper. Thank you very much for watching, and if you're revising for A-level physics, have a browse through my channel. You're going to find videos across all the different topics at A-level that hopefully you're going to find helpful. Once again, thank you very much for watching, and I will see you in the next video.